Okay, good day, everyone. Thank you for joining us for this webinar presentation. My name is John Clements, and I'm the technical lead for the Homeland Defense and Security Information Analysis Center, or HDIAC, one of three IAC domains in the DoD Information Analysis Centers operating under the Defense Technical Information Center, or DTIC, within the Office of the Undersecretary of Defense for Research and Engineering. Our informative webinar series highlights current emerging research and technology developments. It presents an opportunity for accelerating the DoD's leverage of these advancements by increasing awareness and fostering technical collaboration. HDIAC supports those working on the Homeland Defense and Security domains of DoD research and engineering. We do this by helping navigate the vast landscape of scientific and technical information, allowing our customers to get a head start on their technical projects. We provide research and analysis services and help unlock access to information, knowledge, and best practices from government, industry, and academia to stimulate innovation, foster collaboration, and eliminate redundancy. We hope you enjoy this webinar and that it serves as a catalyst for community collaboration and improved DoD Homeland Defense and Security research. But before we begin, I will note a couple of administrative items. First, if you're dialed in by phone and would like a copy of the slides, they were posted to the HDIAC webinar announcement. You can go to hdIAC.org/webinars and find today's webinar. When you click on it, at the bottom of the announcement, it will say to view the PDF, click here. Second, all participants are muted, but you can chat with the presenters and moderators using the chat box to the left. However, if you would like to pose a question for the Q&A session at the end, please use the audience questions tool at the top center of your screen. It is the icon that looks like a chat bubble with a question mark next to the emoji. At the end of the presentation, I will go over the Q&A, and for the benefit of anybody who dialed in on the phone, I will read the questions out loud through the presenter. If you have technical issues during the presentation, don't worry. The full presentation will be available online. Check back to the HDIAC website. Once the webinar is posted, the Go to Webinar button will take you to the YouTube link. So I'd like to take this opportunity to introduce today's presenter. Michael Lambert is an emergency preparedness Homeland Security planner for the Houston-Galveston Area Council of Governments, where he's responsible for assisting jurisdictional leaders in a 13-county region with developing disaster preparedness, response, and recovery plans and capabilities for a wide range of threats. Michael is an experienced emergency manager with a long-standing focus on low-probability, high-consequence disasters, including the catastrophic loss of containment of highly toxic hazardous materials, pandemic, influenza, bioterrorism, and long-duration, widespread disruptions to the electric grid. Michael is a member of the FBI InfraGard National Disaster Resiliency Council and is a founding member of NDRC's Water Security Work Group. He is also a member of the National Secure the Grid Coalition, as well as the Global Resilience Commission. Michael is currently a representative on the Texas Critical Infrastructure Protection Task Force and serves on a number of other regional Homeland Security-related working groups and task forces. Michael holds a master's degree in finance from the Texas A&M University. With that, Mr. Lambert, I will turn over the virtual floor to you and take it away.
Well, for any of you Aggies out there, just know that I was muted and I went whoop when he mentioned Texas A&M. And if you don't understand that, then don't worry about it. It's kind of an Aggie thing. Love introductions. Love the one that a good friend of mine did some years ago. As I said, a very good friend of mine. It was a very large audience. We had a lot to talk about. And his introduction to me was, Michael Lambert is just a guy. Some of the stuff he does is reasonably interesting. And I love that, and I just as soon hear that as any other. But good afternoon, good morning. It's morning where I am, maybe afternoon where you are. Before we get into this, and given the augustness of the folks on this call, I want to make a very clear point. I am not an engineer, nor am I a scientist. I will talk a little bit about some technical stuff, but understand that I look at this whole subject as an experienced emergency manager. And that's where I come from, and that's the basis of this whole thing. So I can answer some technical questions, but if you're going to get too deeply into the technology or the science of it, I'll just have to say, I can't answer that, but I'll get back with you. So that being said, why don't we move forward? So today's premise, I think we can all on this call in particular, agree with these 3 points. The electricity grid is the bedrock of our modern society. The grid that brings the electricity, the grids actually that bring us our electricity, is fragile, and we need to recognize, embrace, and plan for that fragility. So we're going to address those premises, primi, as it were, by quickly running through, well, a little bit more detailed, running through the 2021 Texas grid down issue. What it would today would have been exactly 13 months ago. Then we're going to highlight some other threats to the grid and take a quick look at planning and preparedness implications. So here's a little imagination exercise. I want you to right now imagine on the right-hand side of your screen is a blue pill, and on the left-hand side of your screen is a red pill. Now, those of you will recognize, most of you will recognize the pop cultural reference of the red pill and the blue pill. The blue pill you take if you want to live in the world of the bubble where everything works and you don't ever get a look behind the curtain to see what's really going on. The red pill is the pill that you take if you want to get a really good look at what's going on behind the curtain. And we all like to live in the blue pill world. We get up in the morning in the blue pill world. Most of us do. Those of us in emergency management live in a red pill world, but all of us get force fed the red pill every once in a while. And that did happen back in February last year. So through the many years that I've done presentations and worked on this sort of stuff, I've identified some human conditions that kind of lead to crises and guide how we get into crises. And so I'm going to go through those really quickly to set the stage. The first thing, it's a human condition. This is not pointing fingers at anybody. The first thing is a failure of imagination. And that's the condition where you can't plan or prepare or even imagine some particular instance, some particular outcome, because you just never experienced it or seen anything like it, and you just can't, get there because you just can't imagine it. Then the next one is sort of allied. It's the inability to suspend disbelief. And that's where something could happen, and you might even see evidence of it starting to happen, but you just can't get to a response or in the right frame of mind because you just can't believe it. That happens a lot. And then the number 3 is whistling past the graveyard. That's where something could happen, you're aware of it, you're even afraid of it, but you're not going to take any action to prepare or plan for it because, well, maybe the economics aren't there for your organization, or you have a political issue, some sort of corporate or policy issue that keeps you from it. So you just go forward, kick the can down the road, if you will, knowing that this possibly could happen, but just praying that it will happen on somebody else's watch. So I've lived for a long time talking about these 3, and recently it came to me that there's actually a 4th, and that is the misplaced confidence, the I got this syndrome, or the we got this syndrome, where you don't specifically plan for things that could happen or you're afraid could happen because, well, you've got plans for stuff like that. And you're good and you're talented and your team is talented and we can deal with anything. So the I got this syndrome comes from misplaced confidence. So those 4, I think, set the basic human condition that causes us to miss stuff and causes crises. It doesn't cause crises, but causes us to miss stuff and makes us mishandle crises, if you will. But there are specific traps as regards the grid. There's the all power outages are geographically localized trap. And that is largely true. Power outages tend to be very localized in a geographical area. It's very rare that the geographical area is extremely large. And so far, we in the United States have not experienced a systemic failure across the entire continent or across anything more than just large swaths of the country. There's power outages have a finite predictable duration, and that's largely true. Speaks to how good the folks that bring us our power are. They are able to quickly localize the problem and work around it. That's very true, happens very often, but there are scenarios out there where that wouldn't be true. For instance, the power outage for Texas. As far as I'm able to determine, it is the first time, at least in the United States, that there was ever a power outage that nothing could be done. Once it started, nothing could be done to reverse it until the weather let up and it started getting warmer. Then the utility companies will send an army of workers to fix the problem. We call that the bucket truck brigade, and they will do that. But there are scenarios out there where it isn't just down power lines or blown up transformers. There are scenarios out there where bucket trucks and hardworking technical guys, people are not going to be able to fix that problem. And then, of course, the last trap that we fall into as emergency managers is that our neighbors, the state, and the federal government will send the cavalry. Yes, they will. But it is very possible that they have no additional, your neighbors or your state may not have additional resources to send you. They may be victims of the same problem that you are, and they may not be able to get to you. For instance, the floods that we had down here during Hurricane Harvey, or even the ice storm, help could not get to some people just because there was the ice on the road. And of course, the federal government will do what the federal government does, but it may not be able to get to you for 72 or more hours. So those are traps that we have to keep in mind that we can fall into when talking about the grid. And as we all know, there's not just one grid. There are an awful lot of grids out there. A large number, have no idea how many there are. Different grids, but they're grouped in the United States into independent service organizations, and you see those different colors there representing different organizations that coordinate and manage the generation and distribution of power. The West Coast is the western side's a little bit different, but it's fundamentally the same. Lots of different grids all grouped together. And you'll see poor little Texas down there, or what looks almost like Texas. But we stand alone. We have our own situation, and let's look at that a little closer. This is Texas, and the reason why that previous graphic didn't quite look like the Texas that we all know and love is because Texas actually has 4 different grids. It comes from 4 different places: the Mid-Continent, the Southwest Power Pool, and the Western folks. So the blue area is the one that we're going to talk about. That is the ERCOT, the Electric Reliability Council of Texas grid, and that's the one that we're going to speak of today. By the way, that graphic is a little bit old. They do change over time. This is the most current vision of what the ERCOT area looks like. It's slightly different, but fundamentally the same things, the same issues apply. So let's talk about ERCOT. It's very important to understand ERCOT in order to understand this story. ERCOT, that blue grid, covers 75% of the state and has 90% of the customer base. They have 710 generation units. Now that doesn't include all of the intermittents, the solar and the windmills. It does not include all of those. These are dispatchable generation units. So there are 710 of them. There are 46,500 miles of transmission line under ERCOT's control. I have absolutely no idea how many distribution last mile lines there are. That is, and I don't know that anybody really has a complete handle on it. And besides, that kind of information is rather closely held. So there are tens of, if not hundreds of thousands of miles of last mile distribution lines. ERCOT is largely deregulated or restructured. That happened back in the late 80s, early 90s. We'll talk about that a little bit in a second. It's non-discriminatory supply side. I used to joke that if you had a big enough wheel and enough hamsters to run around in it, you could sell and meet the technical qualifications that you could sell energy to the electric grid, to ERCOT. The truth is, with the new distributed energy sources coming online, non-discriminatory supply side is actually the rule more than it is the exception. Texas produces more electricity than any other state in the country. It also uses more electricity than any other state in the country, and we produce more of the intermittent electricity than any other state in the country. It's getting upwards of 30% of the typical supply is produced by the intermittents. I call them intermittents. Most people would refer to them, or a lot of people would refer to them as green or renewable. You're welcome to do that. I have no problem with anybody who says that. But to me, as an emergency manager, I call them intermittents because the amount of electricity that they can produce is outside the control of human control. It is under the control of the weather, and they produce energy when they want to, essentially. And so they're not dispatchable. And so therefore I use the term intermittent and will throughout this presentation. The state has limited interconnections with the other national grids. There are 4 interconnect lines. They are reasonably trivial. 2 go down into Mexico and 2 go out the east and north side of the state. The ones that go into Mexico are more often used for us to provide electricity to them to stabilize their grid, but we do not take electricity from other grids. We can, but very limited. It's biased to hot weather conditions. Our grid is. It gets very cold in Texas. It's not that it doesn't get cold. It does from time to time, but it is hot more often than cold. And the economic decisions have been made in the past to prepare and build a system to deal with heat as opposed to deal with cold. Now that is evolving over the last 13 months, and it's evolving as we speak. And then the last element we'll discuss here, it is an energy only. It is the only ISO grid in the country that is energy only. And quickly that means generation companies are paid only for the electricity that they produce. There is no payment to any energy or generating company or generating facility for standing by. You get paid for what you make. They bid into the system at their marginal cost, which tends to be or is defined as the cost of the fuel, some of the personnel costs, and some of the maintenance costs. There's no direct compensation for fixed costs. You don't get paid to build. The ERCOT or the grid does not pay you to build capacity. There's no ability to compel the generation. There's no one in the state that can make Calpines or any of the other generating companies actually turn their generators. Can't do it. They are induced to do it by the price and the economics of the system. That particular qualification or dynamic of not paying for fixed costs and not paying for standby generation does cause the reserve capacity in the state to be reduced relative to other grids. That's actually a feature. It's a design feature. It's not a bug. They did that when they designed the system. They did that on purpose. And overall, consumer electricity prices are lower. I believe that's true. I've been told that's true. I've looked at it. It looks true, but I mean, it's always debatable. There may be someone out there who produces energy across their grid cheaper than we do here. But overall, it's cheaper electricity in the ERCOT grid. I want to just quickly throw these up to you. There's the cost of electricity does vary considerably. It typically runs between the $25 and $50 per megawatt hour here in the state. But as you can see on the 21st of February, they were actually paying you to take their electricity, essentially. It was below zero. It does that from time to time. It doesn't do it often, but it does that from time to time. And then, of course, later in that day, it got up into the normal range pretty much for the remainder of the day. Now, 2 days later, on the 23rd, you'll note the scaling on this is different because you look at the line and it looks like it's zero. It's not. It's in the $25 to $50 range. But toward the end of the evening, it spiked up to $1,500 per megawatt hour. And the very next day, in the morning, it dropped back down to the right range. And then in the mid-morning, it spiked to $4,000. So I offer that for two reasons. One, to show you that the price can be dynamic and can be dynamic over a pretty considerable range. And two, to take away any uh, sadness you may have felt for those poor downtrodden generators that they only get paid for their marginal cost, so they don't make any money. That's not the case. They do quite well, and that's a good thing. So the grid participants quickly, there are the bulk generators, as we just talked about. They are unregulated except for the technical elements. The transmission and distribution utilities, they are highly regulated. These folks pick up the electricity that's produced at the generator, at a transformer, and they take it all the way to your meter. At which point comes the retail energy providers. Now, these folks don't own anything. They basically have a contract with you to sell you electricity and a contract with the provider to buy electricity. The amounts that they pay are open to, I mean, it's the Wild West out there. They have all sorts of different kinds of contracts. But retail energy providers are who you pay your bill to, and they do literally nothing but accounting. In the state of Texas, each of the above participants have to be independent. They can be owned by the same holding company, but they can't have interlocking boards, and they have to be operated independently. Now, that, of course, is accepted for municipally owned systems, and there are a couple of very large municipally owned systems in the state, and for co-ops. There are a couple of really large co-ops, and mostly co-ops tend to be small, but there are a few that are quite large. And for the oversight, the aforementioned Electric Reliability Council of Texas is made up of, the board is made up of, and it has changed, by the way. At the time that this happened, it was largely representatives from the grid, the energy companies. I'm sorry, the generating companies, the TDUs and the REPs. It's been changed. It's a little bit different how they go about picking them. There were, in February of last year, 5 at-large board members. None of them lived in Texas, and one of them didn't even live in the country, and that has been changed. The Public Utility Commission of Texas, which of course oversees all of the public utility regulations, that is a 3-member board appointed by the governor. And then, of course, the Texas Railroad Commission is down here in italics. Until very recently, until this year, the Texas Railroad Commission really had no direct input into the electric grid. They all, by the way, also don't have anything to do with railroads. They are the folks that oversee the natural gas. And natural gas is a big fuel source for generation of electricity in the state. And until just recently, there was no standardized working relationship between the Public Utility Commission and the Railroad Commission, but that has also changed as a result. So there's better pictures of this. This one just happens to be outside my house. I live in a townhome complex, literally yards away from the central business district of Houston. That white stuff is not concrete. That white stuff is not snow. That white stuff is ice. We've lived here for 16 years. We've seen snow, we've seen ice, but we've never seen ice that lasted as long as it did this time. I show this basically to make the point. It got very cold for a very long period of time in parts of the state that don't usually see that cold of weather for that long. This particular graphic comes from the National Weather Service. I'm very close to the Houston Galveston folks. Have worked with them for years and used to office in the same building. They are aghast at this particular graphic. This shows something that has never happened before, and that is that every county in the state of Texas, in the state of Oklahoma, in the state of Arkansas, and almost all of the parishes in Louisiana were under a severe winter weather warning. The difference between a watch and a warning is, as I like to say, if my grandkids are here and they have all the ingredients for making cupcakes laid out on the table, then that's a cupcake watch. It means the ingredients are there that could cause a cupcake to happen. But once that cupcake is put together and put in the oven and is cooking, well, that's a cupcake warning. There will be cupcakes. And that right there, that pink area is the area of the United States that was under a severe winter weather warning during this period of time. Let's look at the actual incident. This is the graph depicting the cold weather in three of our major metropolitan areas, Houston, Dallas, and Austin. You'll note it got really cold on the 16th, but that pink or red, depending upon the color that you see, ellipse is one that I added because that's the critical area that we'll talk about in just a couple of slides. That is the critical moment. You'll notice that in the parts of the state, the major metropolitan areas, it wasn't terribly cold. I mean, it was very cold, but it wasn't horrifyingly cold as it got. However, up in Amarillo in the Panhandle, it was already 8 degrees below zero, which looked at another way is 40 degrees below freezing. And that does play into the rest of the story. Quickly, don't pay any attention to the colors on this graph. Just look at the dots and look at the red line. That red line is an approximation of where to the left, to the west of that red line was really cold weather during the period of time we're going to talk about in just a minute. Those dots represent generation facilities. Yes, there are not 710 dots on that graph, but some of those dots represent more than one and actually multiple generation facilities. And you'll note that a big portion of the state's generation facilities was in the very cold weather when things started to unfold and go wrong. Quickly, this graph just shows as the line goes up, that's more generation capacity that goes offline. I put it up here to demonstrate to you that at midnight on the 14th, which is a Sunday, we were already down 25 gigawatts, 25,000 megawatts. We were already down that much capacity had gone offline, of which over half of it was wind and solar, the intermittents. And you'll note, I just want you to note that line continues to go up slowly, but it does continue to go up across the entire day of February the 14th to that red ellipse. And let's talk about that because this is the heart of what happened. And I know this graph is very busy, but it is extremely informative, and it is really the heart of the understanding of what happened. Each of those vertical lines represents 1 minute. Each of the horizontal white lines represents 0.1 cycle per second or 0.1 hertz. The blue line, of course, represents the frequency. Many of you technically oriented probably understand and know what that means. Many of my emergency management friends don't have the understanding, so I tell them to look at it this way. That blue line can be fairly looked at as a representation of the demand to the supply. Think of it sort of like going up a steep hill in your car. As you go up the steep hill, the further up the hill you go, the more work the car is having to provide, the more the engine works, the more strain there is on the engine. And that's roughly, isn't exactly, but that's roughly what that blue line represents. Now, the frequency is a closely guarded, closely tracked dimension of the generation. You'll note that at 1:23 on the 15th, that it was down to really one of the golden numbers, which is 59.9. That is a critical number and causes people to start to get very concerned, the managers to get very concerned. You'll also note that by that time, we lost 35 gigawatts, 35,343 megawatts of generation by that time. The frequency had dropped into this area that causes a great deal of concern. So they laid off 1,000 megawatts. Now, 1,000 megawatts is a lot, but it isn't a great deal across the entire scheme of things. At the time, they clearly were thinking that you could handle that with rolling blackouts, that it was not a severe problem, that it was critical, but it did not come to the level of crisis mode yet. Now, that dotted line arrow ties to the dotted line arrow just a little bit, 16 minutes to the right. And that just shows where they started losing and did eventually wind up losing 1,418 megawatts. That's an additional 1,400 megawatts. That's a considerable amount. They had received some relief on the frequency, but it started to go down again. And at that moment, they were back to the 59.9. A couple of minutes later, they lost a quarter of or 248,000 megawatts, about another minute, 329,000. And the frequency dropped below 59.8 and stayed there for a couple of minutes. And I'm sure started to cause folks inside the control room to get very, very concerned. They laid off another 1,000 megawatts. Again, even the 2,000 that they've laid off by now could be handled by rolling blackouts. It is now getting to be a bigger situation, but it isn't a crisis. And then note that in the next 2 minutes, they lose 606,000 megawatts, 688,000 megawatts, and 511,000 megawatts. And the frequency dives steeply. Now, the 59.4 is a extremely critical number. By regulation and by design, the system really cannot operate below 59.4 indefinitely. As a matter of fact, by regulation, you are allowed to be under 59.4 for only 9 minutes. And at 9 minutes and 1 nanosecond, facilities and equipment starts to shut down automatically. And essentially, it spins down. You lose control. It goes automatically. So you'll notice that they're down in the critical area. They lay off 300 or 3,000 megawatts. They continue to go down, but it does tend to stabilize a little bit. They get down to the lowest point, 59.302. I can hardly imagine what the folks in the control room. Now, they're all highly trained, highly skilled professionals, and by reputation, they don't freak out. But I can only imagine the level of concern they had at that time. They laid off another 3,500 megawatts to try to start bringing it out. You'll notice the little X over there. That's doom. That's where things start to fall apart. Now, from that point on, they got relief on the frequency, but they continued to lay off. They continued to lose generation, and they continue to lay off load. And so this graphic, I added this graphic just recently. Excuse me for missing it. I just want to show you, this is what, on February the 15th of this year, what the frequencies were doing. You'll note that they range between basically 59.975 and 60 point whatever. And those red lines there basically show you the time frame that we saw in the previous graph, where they dropped down to 59.4. Now, back to this graph. That red ellipse is the same thing. Basically, I put this here just to show you that the critical worst, the thing that really caused the crises happened in that time frame, but it did not go away. The blue line shows that we continued to lose generation capability, and the black line across the bottom shows you that they continue to shed load for 2 days more. The purple line is basically a retrocast that ERCOT went back and did and said, if everything had been working correctly, this is our hypothetical demand curve that we see. It's interesting. The difference, of course, is what was shed, the load shed. So how does the load shed work? In the state of Texas, the ERCOT does not say Michael Lambert is a kind of a jerky fella and we need to lay off some electricity, so cut off his electricity. They don't say that. They tell the transmission and distribution companies that they have to shed a certain amount of load, and the amount that they have to shed is based on the percentage, their market percentage. So CenterPoint, which is my provider, has 24.83 percent of the load, or the demand, or the market, let's call it that, in the state of Texas. So they had to lay off 24.83 of the load that was being shed. Yeah, we'll leave that there. So they don't even say, yeah, we don't like that Michael Lambert guy. We want to cut off his electricity. They cut it off at the circuit level. And there are three types of circuits in the grid. There's the under frequency circuits. These are protected circuits. They're put in, technically able to deal in under frequency environment. They are spread out throughout the service area, and in order to maintain some sort of equitable distribution. But they are there to help when there's been a load shed. They are there to help bring the system back online. Then there are the critical loads. That's your hospitals, your law enforcement centers, et cetera. Those are the places that really should not be cut off, and they are the next highest priority to not cut off in case of rolling blackouts or load shed. And then, of course, there's the rest of us, and that's where I sit. The distribution of those under frequency circuits and critical loads is a debatable thing, but the number of the rest of us is pretty well established across all sources of information to be about 50 or 60%. So in theory, 50 or 60% of the customers would have had to bear the load shed, but that was impossible. The fact is that they got up into the critical load. I have no understanding whether they got up into the under frequency, but I do know that critical loads were being cut off. So 2011, we had a very similar set of circumstances. It was the start of the biennial Texas legislative session, and they got very concerned about it, and they went into session and produced a whole bunch of laws and regulations so that we would never have that happen again. Well, 10 years later, it happened again. And with all of that regulation and changes in the law, just look, there was 3.6 times as much generation capacity went down, 1.8 times 1.8 times as many generators went down. The cumulative frequency got down to 59 points, or the low frequency got down to 59.3, which is incredibly low. The duration of the load shed was 9.4 times as long as it was in 2011. And the estimated peak load without the shed was 130% of what it was in 2011. Just showing you, not trying to cast any aspersion or point any fingers, that what they did in 2011 either wasn't appropriately implemented or just didn't work, because 2021 was much worse. So the impacts, there are all sorts of estimates. I think the official state estimate now is 265 people died during that period of time from the cold weather. Let's be perfectly frank, and people, when it gets that cold in the state of Texas, people die. To me, that's rather anathema to my reason for being an emergency manager, but it is true. People die in this state when it gets that cold for that long. However, it is nowhere near 250. The vast majority of the people who died during this time probably died as a result of not having electricity. 4.5 million meters were without power. Now, we all know that the meters are just represent the customer. That doesn't represent the number of souls. You can get into a pretty good debate on the number of souls that were without electricity. Based on the calculations that I'm able to come up with, it's north of 10 million people. 10 million people didn't have electricity as a result of the power outages. At least 12 million people were without water. Just like the people die when it's cold, that cold in Texas, water systems fail, but not to the level of 12 million people. Supply chain across the state was disrupted for all the reasons you might imagine. Control systems were down because the electricity was down, and there was ice on the road. So we had real supply disruptions. And then any of you who have spent any time around the petrochemical industry know that the scariest thing that can happen in a refinery or a petrochemical facility, pardon me, is for the electricity to catastrophically fail. I have a picture, but we don't have time to show it, of what it looks like when a refinery loses electricity. They don't blow up, but they start to flare, and it looks like something that Dante would write about. So the instant miss that there was chaos, no, there was not chaos. There were lots of chaotic situation, but overall there was no chaos. The grid collapsed. No, it got really close to collapsing, but it did not collapse. It stayed up and running and was able to come back when the weather abated. The weather decimated the transmission and delivery system. No, that didn't happen either. It's estimated that about 10% of the transmission delivery system, or about 10% of the problem, was caused by down power lines or things that happen with the sticks and wires. The demand exceeded the total generation capacity. No. Even without the intermittents added in, there's 107,000 or more megawatts of generation capacity in the system. Now, that number is a blue sky, wonderful day kind of capacity, but there was more than enough total capacity. There just wasn't enough available capacity. The interconnections with the other states would have saved the day for the state of Texas. No, none of our other partners, or our partners to the states and all, had any extra electricity to send us. In this particular case, maybe in some cases it would help, but in this particular case, the interconnects would not have helped us. The failure of the intermittents caused the problem. That was a big early on consideration down here, but that's not it either. The intermittents did not help, but they did not cause the problem. We'll talk about this slide very briefly because I'm a little long-winded here. That 100% line there represents the not the total capacity of any particular fuel source, but the total capacity, or the total that was expected in ERCOT's severe winter weather plan. They did have one, and they're required to. You'll notice the green line, they did pretty well until they didn't. And then for almost the entire period of the load shed, they were not providing any help to the grid. You'll notice that the line that runs across the 100%, that's the nuclear. We have 4 nuclear generators here. One of them went down, so we lost 25% of the capacity. And then, of course, there's a blue line, kind of hard to see in this graph, but there's a blue line that represents the natural gas, and that's what was, the real problem here. The natural gas system just basically failed. A couple of reasons for that. One, natural gas, when it comes out of the ground, is very water laden, and it froze. It actually froze in the distribution pipes, and it froze at the wellhead. So natural gas wasn't there to be to power the generators. There are a couple of other reasons too. A few of those, or most of those generators, were not on the do not cut off list on the critical load list, so they got cut off like everybody else. And there are others, but those are the primary reasons. So let's move along and move out of the discussion of the Texas issue and move into what we see as other threat vectors, other vulnerabilities in the system. Of course, there's the natural threats. We've discussed the weather at length. Very hot weather, components fail during hot weather. Wires sag, get close to the ground, and short out and shut down distribution. Very cold weather, we've hit that pretty hard. Very cold weather will also cause the transmission and the distribution system to fail because, well, sometimes they just collapse. Very windy weather will cause the lines to sway and short out. Very wet weather will flood the facility, the transformers and other facilities. Wildfire, of course, can create its own problems from burning stuff up. Earthquakes, I think we can all understand what an earthquake would do to a delivery system or to a generation system. Of course, I'd love to be able to go into a deep, dark discussion of the coronal mass ejection, geomagnetic disturbance that can be caused by the sun. It's worthy of some consideration, but we do not have time to discuss that at the length that it needs to be discussed. Then, of course, there are the human-made threats, sabotage. There's an increasing amount of concern that some of the components in the grid may be infected with cyber issues. There is an increasing concern that there may be some backdoors and some of the very critical very critical components that are are not built in the United States, are provided by other countries. The coordinated physical attack, look up Metcalf, California, about 5 or 6 years ago to get a pretty good in-depth understanding of the potential cascading failures from a physical attack on transformers. Coordinated electromagnetic interference. I'd love to spend 20 minutes talking about this, but it is simply the ability to build a magnetic interference device and shoot it at transformers and the like and cause them to have problems, again, causing a cascading failure. High altitude electromagnetic pulse, that's another one that we could spend hours, and I do in other presentations spend a long time talking about, but I'm thinking this group probably understands that threat. And then cyber attack, very hot topic now. Technical threats, well, we've seen, when we talk about improper design, it could be the improper technical design, but also the systemic design. We could draw some of the problems in Texas last year and actually cause it improper design. Clearly, we can call a lot of it component failures. I'm not so sure about operational errors. I don't want to get there, but operational errors can cause and have in the past caused dramatic blackouts. Quickly, the grid is undergoing some really dramatic and time compressed changes just now. But it faces these structural challenges. There's aging infrastructure out there. Some of those components are very old. Now there's new stuff being put on, in place also, but some of that infrastructure is very old and has, and is being overlaid by and being asked to do a whole bunch of new stuff that it wasn't designed for. The growing demand, culturally and politically, we are pressing the grid to take on demand through electrification that it's not designed at this moment to do, and quite possibly is not prepared to do. Pressure to move to intermittent sources. The next two basically go together. The pressure to move to intermittent sources and away from the stable generators that use fossil fuels is putting a lot of pressure on the design of the grid. The IT-OT convergence, information technology, now being merged with the operational technology. Things that used to live in two different universes are now being forced together and creating a lot of potential problems from cyber attacks and others. Again, a subject worthy of considerable discussion. And then, of course, we've already talked about the growing complexity of the system. Takeaways: the grid can fail. We know that. Secondary generation sources, your generators will do you well for a little while, but they are insufficient to the task. Just-in-time resourcing is not your friend. We got a really good taste of that with COVID, but in a blackout situation, a widespread, long-duration blackout, just-in-time resourcing, which is economically friendly, is not disaster-friendly. We discussed that your neighbors very well may not be there for you, not because they don't love you, but because they can't be there. And no matter how well and prepared you are, you aren't. Finally, a couple of things to think about. We'll run through these very quickly. Long duration, widespread power outages should be considered in public policy, and that is something that is beginning to happen at the national and state level. It needs to be drilled down to even lower levels. It needs to be included in strategic planning at the lower jurisdictional levels. Jurisdiction and government agencies need to do impact assessments. Again, I'm talking more of the local jurisdictions and state jurisdictions need to assess their AORs to see what the impact of a long duration power outage would be. Emergency operation plans need to be modified to include a long duration widespread power outage. Jurisdictional leaders need to develop relationships with their utility providers. That was a really shocking thing. There is a lot, but it's not universal. There are lots of jurisdictions out there that do not have any understanding of who their providers are. And they need to know that, and they need to know their regulators, and they need to have a relationship with them so that they don't meet on the side of the road at 4 o'clock in the morning responding to a disaster. The appropriate organizations need to be on the critical load list. I could go through a list of people who contacted me after this was over and said, hey, how do we get on the critical load list, and that list included a large number of law enforcement agencies. And then, of course, jurisdictions need to establish the supply chain working groups. We are doing that here in the city, and it is a valuable thing for us. So, you have to think of a disaster sort of like water. Um, any crack in your preparedness, any crack in your vessel, water will get in and it makes a big mess. So we need to be prepared. We need to look at these things that seem like one-offs, that seem like black swans, but really aren't. They really could happen. Now, I raced through the last portion of that. I apologize. I am very long-winded. I am very passionate about this subject. I am also very available. By the way, that is me before COVID. I have hair and a beard now. I'm very available and will answer any questions offline. I'll even do this presentation again if you have a group that you want to see it. I think it's an important subject, and I'm available to answer your questions now. I'm available to answer your questions offline, and I'm available to talk to you about any of these subjects. I do appreciate the opportunity to do this. As I said, I apologize for being long-winded. That's just my nature. So at this moment, I will stop and take questions.
Great. So we do have a few that came in. I will post them up on the screen here, but I'll read them out loud for the benefit of people on the phone. So first question, it has been stated that the U.S. has one of the worst interconnected electrical transmission systems in the world, and that will haunt the U.S. in attempting to increase the use of electricity to assist in solving the climate crisis. Is that true?
Oh, that's way outside my lane.
Okay.
Calls for a judgment that I am not expertise to make. I will give you an opinion, and I want it very much to be noted as an opinion. It could be better. I don't know whether Texas benefits or not from not being part of the larger grid, but I can tell you that from my perspective, uh, it could be better. And I'll stop there because I really am out of my lane if I were to ask that question.
Fair enough. Thank you. I'll go on to the next question from Mike Matthews. Are there any microgrids in Texas? And if so, how did they fare?
The answer is microgrids are beginning to take hold in the state. There are some very, very vocal proponents. From a public policy perspective, um, they have not taken hold. I don't know of any public policy that precludes the ability to build a microgrid. Texas is just an unusual case. I talk to people all the time. Microgrids are taking hold throughout the country, not so much in Texas, but that doesn't mean that they're not here. It just means that they're not omnipresent yet. And I couldn't speak to how they fared. I don't have any information on that. I would assume if they were based on solar and wind, they probably didn't fare very well. But that's the best I can answer you, Mike.
Thank you very much. So the next question from Arthur Robinson. As a result of the grid problems due to extreme weather, did the state of Texas invest in upgrades to the grid system short and long term? If so, can you give a project upgrade estimated cost?
To the second question, no. Again, outside my lane, and two, it's ongoing. To the first question, well, as I mentioned, this happened at the very start of the bicameral legislative session. There was lots of sound and fury about how they were going to legislate and make things change, just like they did in 2011. They did come up with some, at the end of the day, they did come up with some not insignificant, non trivial changes, but they didn't quite reach the level of what their rhetoric was in the beginning. So we didn't talk about the economics. That's a subject that's near and dear to my heart, but we could spend days talking about the economics. There were some tremendous financial dislocations in the billions of dollars, multiple billions of dollars caused by this incident. One of the things that they did uh, legislate is to make loans and grants available to the grid providers to um, upgrade and harden against cold weather. And they, by the way, they also put into place some legislated regulations that require them to be hardened against the cold weather. It remains to be seen how that actually gets implemented. But there were billions of dollars in terms of losses. I showed you where the cost of electricity went to $4,000 per megawatt hour for a very brief period of time. In the state, the cost of electricity, the generation of electricity went for about 76 hours, was set at $9,000 per megawatt hour. Every megawatt hour cost $9,000 to buy. So you can imagine over 76 hours what that did. There was billions and billions of dollars of dislocation, and they're still trying to weave that through. So I can't answer your question directly, your second part, but I can tell you that there is movement toward hardening the grid against the cold weather.
Great, thank you. The next question, actually, I submitted. I sat in on this briefing with you before, where you mentioned issues with backup generators. Can you just kind of quickly touch on that from I think more of a preparedness perspective?
Sure. And I took that slide out. I love that slide. But as you recall, you sat through that presentation, which was scheduled to be 40 minutes, and it went an hour. So yeah, I had to cut something out. So the backup generators, if I can recall, basically I was talking about make sure, well, first of all, your backup generators are not going to help you too much through a situation like this. Some of them may, most of them won't. I think I talked about dual fuel sourcing. That's critical. I was part of, for a previous organization, we built a new facility. We put in two very large generators. We made them natural gas, and we thought, wow, we did a great job. We may not be able to get diesel, but we can by God get natural gas. And that turns out to not be true. So your best generators are biofuel sources, whatever, two fuel sources, but you really do need to do that. The other is that you need to test them, and you need to test them regularly, and not just turn them on and see if they will turn on. That's really not relevant if they'll turn on. I think I used the point that as a young person, I had a car that you turn it on, it sounded great. It was a wonderful sounding car. You put it in gear, and it didn't go so well. So you have to significantly test your generators regularly under load so they don't fail you. We can talk for another 20 minutes about the generators at critical facilities in the city of Houston, including the Houston Public Health, where the generators went down and put COVID vaccines at considerable risk. So do that. And I know there were a number of points. I think that's basically the important ones. Dual fuel, test them. And I'm sorry, I can't remember all the elements on that slide, but those are the critical ones that I think you should think about.
Thank you. Now, do you know how, from Scott Armstead, do you know how military facilities fared?
No, I do have some insight into it, but I can't make a definitive statement on that. Some of them down in the southern part of the state have their own capacity. And by the way, down in the southern part of the state, they were not as hard hit. Now, they were hard hit, but they were not as hard hit. And some of those were on the critical load list and were able to stay up. I do know that Joint Base San Antonio is 2 years, actually 3 years into a program of hardening their grid against EMP. It's a study program and a test. But I don't know. I know that NASA is here in Houston and they continue to operate, but they have cogeneration and generation facilities of their own. And I do not know specifically how they made it. So some of them went down, some of them didn't. I'm assuming that most of them were on the critical load list and survived well. I have not heard anything to the counter to that point.
And it looks like we have one more question in the queue
Sure.
right now. So from Joel Hewitt, Which generation source, if any, is least susceptible to downtime due to extreme cold?
I would say diesel and treated gasoline, treated diesel and treated gasoline. Um, Natural gas that's been treated, natural gas froze before it got to the compressor and treatments, okay, to treatment facilities. It froze before it got there. It froze as it came out of the ground and in those transmission pipelines. Once it gets to the treatment facilities where the water is removed, it should be dry enough to hold on or to stand up against the cold weather. But the problem is that if the generation facility or the compressor facility itself isn't generated, then it won't be able to compress it and move it along. So I'm nowadays, after having been such a big proponent of natural gas, nowadays I'm a little bit skeptical of natural gas. It's hard to store, you know, and that's a problem. You can store tons and tons of diesel. You do run into some, regulations about storage, but you can warehouse a lot of diesel, a lot of gasoline, more than you can natural gas. I hope that answers your question, Joel.
All right, sounds good. And that was the last question. So with that, I think this concludes the webinar presentation for today. Again, this was Mr. Michael Lambert. If anybody needs to get a hold of him, I think his contact information is still there on the screen. But if you can't write that down, please feel free to shoot us an email at HDIAC. You can reach us at contact@HDIAC.org, and we can get you in touch with Mr. Lambert. And again, Mr. Lambert, thank you very much for this presentation. It was easily as informative, if not more so, than sitting through it live. So I do appreciate your time and look forward to running into you again this upcoming year.
Well, thank you so much. And listen, I too truly appreciate the opportunity to do this, and I just want everybody to know that this I'm as I've said several times, I'm nearing the end of my career, and this is a passion for me. And anybody that wants to talk about it, wants to hear it again, wants to make criticism or give me helpful comments, I am absolutely there to hear and be there for you. So thank you so much, and y'all have a great day.